All right, guys, so let's talk lesson 5.4 in your packet, talking about simplifying radicals. So in your packet, this is page 18. All right, so first off, we've already done simplifying radicals before back in Unit 4 when we were doing quadratic formula and all that, but we just did strictly numerical and square roots. So now we're going to talk about how to simplify any radical depending on whatever the index is. And it's not just going to be numerical, it's going to have some variables in it as well. But the concept is still pretty much the same. So just to recap, remember when it comes to a radical, you have your index, which is that little number outside the radical that tells you what type of power it's undoing. Your radicand, which is the value underneath the radical. And your root, which is what can come out from under the radical. So for example, if I did the square root of 4, my root would be 2. If I did the cube root of 27, my root would be 3. Now, your index in the radical tells you how many times you have to multiply the root by itself to get the radicand. So r to the n power gives you x. So for example, if you have the square root of 81 is 9, 81 is the radicand, 9 is the root, and the index is 2. Thus, you would have to do 9 times 9, which is 9 squared, which is equal to 81. So let's do a couple of examples like that. So in this case, the radicand is 64. The index is 3. And if I take the cube root of 64, it would be 4. Because if you do 4 times 4 times 4, it's the same thing as 4 cubed, which is 64. Now, our index for the next one is 5, and our radicand is 32x to the fifth. So in other words, we're undoing a fifth root. So we got to think about what number, if we undo a fifth root, would give us 32. So in reality, that's 2, because 2 to the fifth is 32. So our root is 2, but that's not the only part of the root. We also got to consider the x. So x to the fifth, well, if we're undoing a fifth, it would just be x. So our root is 2x. It's 2x times 2x times 2x times 2x times 2x. It's the same thing as 2x to the fifth. Make sure you got those parentheses around it, which is 32x to the fifth. Now, your calculator can do this, but for some of the more simple problems, you should be able to figure them out in your head. So, for example, for number 1, negative 1,000. Well, it's a cube root first off. So for any odd index, you are allowed to have negative numbers under the radical because it would actually give you a negative number if you cubed a negative number. So in reality, you just got to think of what number cube gives you 1,000 and then slap a negative on it. And that would be negative 10. Plus or minus the square root of 44, that's just 12. Or plus or minus 12, we got to throw that plus or minus in front of it. All right, now, square root of 81 and x to the 20th. So we know square root of 81 is 9. Now, the way to undo a square exponent is just like if we were doing x to some power, let's call it a, all squared. We know power rule is you're multiplying that 2 to the front. So we have x to the 2a. Well, if you're taking a square root, that's the same thing as if we turn to a fractional exponent, so 1/2. So what happens is that if you multiply 2a to 1/2, you get 2a over 2, which is just a. So in reality, you're either multiplying 1/2 or you're dividing that exponent by 2. So if I divide 20 by 2, I get x to the 10th. Square root of 49 is 7, so I have negative 2 times 7, which is just negative 14. Now, we know that the square root of a negative number is going to give us an imaginary number. So remember, that's when you got to take your I out. So we have I square root 25, which is just 5i. Now, x squared y to the 22nd z to the 0 power. Another way you can think about this, if you forget to divide those, you can also change this to be fraction. So all of this raised to the 1/2 power, where you would distribute 1/2 to all of those exponents. So that would be x to the first power, y to the 11th, and then z to the 0. And remember, z to the 0 power is just 1, so this is just x, y to the 11th. Fifth root of negative 32, again, we have a odd index, so we can have a real negative number be our answer. So whatever the fifth root of 32 is, we just slap a negative onto it, which in that case is negative 2. X to the 4th. So if we think about it, we can rewrite this as x to the 4th raised to the 1/2. 1/2 times 4 is 4 over 2, which is 2, so this would be x squared. Last one. So we have the negative 2, and it's going to be multiplied to square root of 16, which is 4. A to the 10th, we can just divide 10 by 2, get a to the 5th. B squared, 2 divided by 2 is just 1, so b. So, and then we have to just clean it up. So negative 2 times 4 is 8. Negative 8, a to the 5th, b. Now, those are some very simple ones, but when we get more into difficult values, I will show you what to do with that. So for right now, we dealt with perfect squares, perfect cubes, perfect fifths, perfect fourths. But in the next little bit, we're actually going to talk about what to do when you don't have those perfect squares or fifths or fourths. All right, so let's think about these next two carefully. All right, so our radicand for this first one is 1296 m to the 4th into the 8th. Our index is 4. And we'll come back to the root in just a second. So, when it comes to the roots, all right, sometimes it's hard to figure out what it is. So, we are going to discuss how to do a factor tree. And we kind of already discussed this back when we talked about simplifying. So, what we do is that I really am more concerned about the number. So, I'm going to do 1296 and I'm going to break it down into two factors. All right, and you can use a calculator for this. I always start with 2 because that gives me an idea of where to start. So I'm going to divide 1296 by 2 and I get 648. Now, 2 is prime, but I can break down 648 further. All right, so I'm going to divide that by 2, get 324. Divide it by 2 again. Divide by 2 again, I get 162. And I'm just going to keep dividing by 2 until I get a number that I can actually see. Then 2 again, and I get 81. Now, we know that 81 is a perfect fourth, all right, because it'll break down into 4 threes. So 81 is a perfect fourth. But if you also look, we have 2 twos, or not 2 twos. We have 4 sets of 2, all right? which means 2 times 2 times 2 times 2, that's also a perfect fourth. So if we multiply all 4 of these together, we would get 16. So if I wanted to rewrite this fourth root, because remember, we're looking for pairs of 4, and if you need to, you can break down the 81 further into 9, 9, 3, 3, 3, 3. And as you can see, there's 4 3s. So sometimes breaking it down into your 5 factors or your prime factors actually gives you an idea of what needs to come out. So we have 4 2s and 4 3s. So we can rewrite this as the fourth root of 16 times the fourth root of 81 times the fourth root of m to the fourth times the fourth root of n to the eighth. And then we just need to simplify. So we know the fourth root of 16 is 2. Fourth root of 81 is 3. If we change this to be m to the fourth times 1/4 multiplied together, that would just give us 1. So that would be m to the first, or you could just divide 4 by 4. So that would be m times n to the eighth raised to the 1/4. 8 times 1/4 is 8 over 4, which is just 2. Or you could just divide 8 by 4 and still get the same thing. So this would be n squared. And then we just clean it up. So our root would be 3 times 2, which is 6, m to the n squared. So this would be 6mn squared. All right. So give this second one a try. And it's a little bit easier because you should already know what 144 is. All right. And in the notes, I will have this part filled out. But give that one a try on your own and cross-check it with my PDF version of the notes. Now, just to kind of recap what I did with the factor tree. To make a factor tree, you start with a number and you just find 2 factors of that number. It doesn't matter what. If it's an even number, sometimes using 2 is your best bet. Then you group the factors into groups based off of the index. So you could do it like we did when we were simplifying square roots, where you find the perfect squares to pull out. But if you're doing things like fourths and fifths and thirds or cubes, sometimes that can be a little bit difficult. So if it helps, you can always break them down into their prime numbers like I did here. And then group them based off the index. So the index is 4, so there's 4 2s here. And then 3 3s here. But I also knew that 81 was a perfect fourth. So I could have stopped there. And then you just pull out one from each group. So in other words, this actually tells you when you take the fourth root what you would get. So you would get 2 and 3 as part of your perfect fourths. And again, but not every problem will work out nicely. So, for example, 48, fourth root. 48 is not a fourth root. It's a perfect cube, but it's not a perfect fourth. So if we try using our calculator to find an exact answer, you won't actually get it. But the best we can do is the radical form, which they did as 2 to the fourth power. 2 to the, and then they take the fourth root of 3. Now, how they do that? Well, let's just do a quick factor tree. So we're just going to find factors of 48. So I have 6 and I have 8. All right. Now, neither one of those are perfect fours, so I'm just going to break it down further. So I have 3 and 2, and then 2 and 4, and I can break down the 4 further to 2 and 2. Now, all of these are my prime factors. So the bottoms of all the branches are your prime factors. So in other words, if your number has another branch or connects to another branch below it, it is not a prime number. And I'm looking for the number that repeats at least 4 times, which is 2. So that means that I would take this 2 out, and whatever I have left over, which is this 3, that's what stays under the radical, which is what they did here. And again, you can do this with variables, you can do it with numbers, whatever. So for example, square root of 12, you can break down 12 into 3 and 4, which we talked about. Since that's a perfect square, you can just rewrite it as 4 times square root of 3, which is equal to square root of 4 times the square root of 3, which is just 2 square root of 3. You could also break down the 4 a step further to be 2 and 2, which if you notice, there's our perfect square, and then the 3 is what was left over. Either way works. Same thing with 24x to the 5th. We're looking for perfect cubes. So with 24, I would break it down till I get a perfect cube. So that'd be 3 and 8. And I know 8's a perfect cube. So if I wanted to rewrite it, I could rewrite this as the cube root of 8 times the cube root of 3. Now, as for x to the 5th, you want to get to an exponent that is a factor or a multiple of 3. Sorry, not a factor, a multiple of 3. So in other words, if I divide it by 3, it will go in evenly. So the closest I can get with x to the 5th is x cubed. So I can rewrite x to the 5th as x cubed times x squared. So I can then do times the cube root of x cubed times the cube root of x squared. Now, if I want to break this 8 down further, I could break it down into 2 and 4, 2 and 2, and just like that, there's my group of 3, and I'm left over with a 3. So if I do some simplifying over here, this is 2 times the cube root of 3 times cube root of x cubed is just x times cube root of x squared. Then I'm just going to do some rearranging so I can combine these two under the same radical and just make sure I write the 2x in front of it. So this would be 2x cube root of 3x cubed squared. And again, that product rule really does help us with radicals. So if you have something times something under the same radical, you can break it up into 2 or vice versa. And this works for perfect squares. This can work for perfect cubes, whatever. So if I want to solve these using the product rule, all right, square root of 8 first off. So I make my factor tree, and I need to find a perfect square to rewrite. So this would be 2 and 4. 4 is my perfect square. So I'm going to rewrite this as the square root of 4 all over the square root of 2. So this breaks apart into the square root of 4 times the square root of 2. Well, square root of 4 is just 2. This would be 2 square root 2. All right, let's try another one. So number 2, we're still taking a square root. So I'm going to do the number first, and then I will add in the variable. Sorry, my computer did a stupid real quick. Hold on 1 second, guys. Apologies for this. Okay, so guys, I gotta restart my computer, so there will be a second part to this video, so just go watch the second part.